Hi everybody, welcome back. This is part 2 on that section in your book called Properties of Logs 10-3. You may need to go back and review part 1 if any of this looks like it's a little over your head right now. Go back and review those earlier sections. I want to do a couple of problems that you had on your homework, and I'll do a couple of story problems as well. This is a type of problem that your book will give you where they're seeing if you know how to use the properties. And so they're going to give you some approximate logarithms here, and they're going to ask you to find, in this case, log base 5 of 50. So you're being asked to find a creative way to express 50 using the numbers 5 and 2 and 3. And I look at this at first glance and I go, well, how about if we call this log base 5 of parentheses 5 squared times 2. There's 2's and 5's, that works. 25 times 2 is 50. Okay, well then, since the request is to multiply, we're going to go ahead and write this as the sum of logs. It's that property that says when your request is to multiply, you can write it as the sum of logs. So this is log base 5 of 5 squared plus log base 5 of 2. Now there's also another property that says when you take a result that's being raised to a power, you can drag that result around to the front and multiply. In other words, the request is to power, so you find yourself multiplying the exponent. So I drag it around to the front here and multiply it since its powers of powers here. And then this is log base 5 of 2 still. All right. Well, let's review that. This is right here log base 5 of 5. Well, that happens to be 1 because a log base 5 and 5 undo one another. It's asking the question, what is the exponent on 5 that will give me 5? Well, it's got to be 1. So this is actually 2 times 1 plus log base 5 of 2. They give us it up right at the top up here, 0.4307. And we find that our answer is 2.4307 approximately. Let's take a look at another one. All right, let's take a look at the division property of logarithms. And I know it's going to be division because there's a subtraction here. If we find ourselves subtracting 2 logs, the request must have been to divide those results from one another. So this is actually log base 2 of this, which is positive. Out front here, it's positive, divided by this, which is negative. Okay? So if we find ourselves subtracting, the request must have been to divide. All right, now when there's a log on one side, we're going to have to jump back into the exponent world. This is one type of problem. You'll look at a different type of problem next where there's a log on both sides. But right now the log's on one side, so we're going to have to jump back into the exponent world. So let's drag down the result and set that equal to throw the base to the other side and bring down the exponent. This exponent comes down right here. Okay. Now to solve this, I have a b squared. That means I may end up with a quadratic here. So let's cross multiply. This is 4. I'm just going to erase that. Now let's leave it there, I guess. And let's 12b minus 2 over b squared minus 3 equals 4. Now if I cross multiply, this on the bottom gets multiplied over here. I have 4b squared minus 12. Okay, since this is a quadratic, it's got x squared here, or b squared, we're going to have to set this equal to 0. So I'm going to move both of these over to the left by subtraction. I'm going to move them over to the other side. So I got 0 here now, and on the right I got 4b squared. This moves across and becomes negative 12b. And let's see, that's supposed to be 21. I didn't bring the 21 down. And this moves to the other side, and adding 21 to both sides, I get a positive 9. Now, as I look at this, we're out of room. I'm going to have to rewrite it over. It looks to me like a perfect trinomial square, so I'm going to go ahead and put it at the top of the page. All right, I put it back up at the top here now so we can continue to solve this. But I've left the original problem up here because, remember, we've got to check these answers to see if they work in the original problem, and it turns out it makes a difference here. I recognize this is a perfect trinomial square, possibly. Let's do the 3 checks. First check, is this a perfect square? Yes, it is. That would be 2b. So multiplied times itself. And the last term is a perfect square, so the square root of that is either 3 or negative 3. And if I multiply the inside and outside terms together, I get 6b and another 6b. Well, I need a negative 12b, so this would have to be a negative here. So I get negative 6b and another negative 6b gives me a negative 12b. So in fact, this is a perfect trinomial square, and this is the way in which it factors. Now, the zero product property says, oh, if the result is 0, then one or both of these has to be 0. Well, since they're identical, we're only going to set one of them equal to 0. The answer for both of them would be the same. Adding 3 to both sides and dividing by 2, we end up with b is equal to 3/2. Now, that looks like a good answer, except we haven't checked it back in the original problem. So I'm going to go ahead and check it back in this one. I probably got to check it back in that one too, but let's find out. 3/2 is b squared. Well, 3/2 squared is 9/4 minus 3. Well, 9/4 is 2 1/4 minus 3. Oh, that's going to give me a negative answer. That's not allowed. I can't do that. It means that this is an extraneous solution. I could check it back up in here. It turns out it doesn't work there either, but it doesn't matter because if one of these is negative, then b cannot be that term. All right, let's try a different problem here. All right, let's try this problem, and this is one that will be on your future assignment here tonight. Notice we've got a log on both sides here, and I want to try to write this string of logs as a single log. Well, I know I can do that using the properties of logarithms. Okay, if a log is positive, it becomes a numerator, and if it's negative, it's in the denominator. So I'm going to rewrite this as log base 5 of 64 is going to go on the top. Negative, so 8/3 will go on the bottom. And positive here, so 2 has to go as a multiply. So as the request is multiply, we add the logs. When the request was to divide, we subtracted logs. Or thinking the other way around, if we find ourselves adding, it must have been multiplication. And if we find ourselves subtracting, we must have been dividing by that. So there it is, and that's the property of logarithms. Now, first of all, this 8/3 in the denominator looks a little strange here. But what I'm going to do is multiply top and bottom of this fraction by the reciprocal, 3/8. Well, what happens when you multiply a reciprocal? Well, these 8s are canceling, the 3s are here as well, and we end up with 64 times 2 times 3/8. Okay? Just a little bit of compound fraction work. Well, I see that this will be some cancellation going on here. So this is log base 5. 8 cancels 64 and makes it 8. And I end up with log base 5 of 48. That's 3 times 2 is 6 times 8 is 48. Now, this problem, because there's a log on both sides, I can set the results equal to each other, unlike the other problem where we had just a log on one side, we had to turn it into exponential form. Here's where we're able to jump out of the log world because both the results are the same. So 48 is equal to 4p, or p just has to be 12. Now we better go back and check that in the original problem. So we look back up here at the top, looking for p. There it is, 4 times p, 4 times 12 is 48. That's a positive number, so this is okay. All right, you'll have that problem to do for tonight and some others. Let's take a look at some word problems. All right, let's take a look at this problem. This is one of the word problems for tonight. If you recall, we had an earthquake formula. This is going back to page 537. They didn't really have it in the problem itself here. But that formula is the magnitude of the earthquake is equal to log base 10 of x, where m is the magnitude in Richters, and x is the amplitude of that seismic wave. You know, how big is the wave, okay? And tells us how tall the wave is. Now, problem 37, I'll read it. It says, the Great Alaskan Earthquake in 1964 was 100 times more intense than the Loma Prieta earthquake in San Francisco in 1989. Find the difference in the Richter scale magnitudes of the earthquakes. Well, Alaska was 100 times San Francisco's. Okay, so we found the magnitude of Alaska and the magnitude of San Francisco. We want to find the difference of the two. So Alaska, here we go. The magnitude of Alaska is log base 10 of 100. Let's say 100. If we let San Francisco be just 1, let it equal to 1. And then the difference of that and the earthquake in San Francisco, log base 10 of 1. Their difference, okay? This is the earthquake in Alaska. This will be the earthquake in San Francisco. Now remember, we're just finding a ratio one to the other because it's 100 times. Technically, we could have just gone 100 over 1. Well, we could have written it that way, but would have ended up looking like this, wouldn't it? Okay, they look exactly the same. It's a ratio of 100 to 1. Well, what is this? This is 100 can be written as 10 squared. And 1 can be written as 10 to the 0. Well, 10 to the 0. Well, that's just 1, isn't it? So I'm going to drag that exponent around to the front, 2 log base 10 of 10. Drag this 0 around to the front, 0 times log base 10 of 10. Now remember that the log base of something and a base, they undo each other. Those undo each other and just become 1. A log base and a base, if they're the same, they undo one another. So this is simply 2 times 1 minus 0 times 1, or our final answer here is the magnitude difference has to be 2. The difference between the two is a magnitude of 2. So if somebody was to look at this on the Richter scale and say, oh, the Richter scale is only difference by 2, how much could that be? Well, it turns out the seismic wave is 100 times taller. If the San Francisco earthquake, the magnitude of the size of the earthquake wave would have been 1 inch, the Alaskan earthquake would have been 100 inches. So that's a difference between the size of those waves. All right, let's take a look at a different problem here. All right, if you remember before that we said that pH is also logarithmic scale, uses a logarithmic scale, just like earthquakes and sound. So let's take a look at a pH problem. Of course, you remember that pH happens to be that scale where on one end of the scale is things that are acid, on the other end of the scale are things that are base or alkaline. And in your science class, you notice that it goes from like 1 to 14, and 7 is like neutral. This particular problem we're going to look at here has to do with blood in the human body. So it's pretty close to the middle. And so, but we're going to find out what the ratio is here. Let's take a look at the problem. I'm reading from page 544. The pH of a person's blood is given by this formula right up here, where B is the concentration of bicarbonate, which is a base in the blood, and C is the concentration of carbonic acid. So it's this ratio of bicarbonate to carbonic acid. Question 11 says, use the quotient property of logarithms to simplify the formula. Well, if I'm going to simplify this formula, I just need to recognize that when I'm subtracting exponents, that's just a ratio. So the pH is 6.1 plus this ratio, log base 10 of B, which is positive in the front, so that goes on the top, and C, which is negative, which makes this go on the bottom. So there's the formula rewritten, and that's in fact what it is. It's a ratio between the bicarbonate, the base, and the carbonic acid. It's this ratio between the two. Question number 12 goes a little farther and says that people have a have a blood pH of 7.4. Notice how close that is to the middle. It's pretty neutral. What they want us to find is the approximate ratio of bicarbonate to carbonic acid for blood with this pH. All right, well, let's put that in for the pH here, 7.4. And then we're going to use the formula here to solve for this ratio. You notice it's asking for what is the ratio. Okay, well, they just need this ratio here. So we're going to solve for B over C. We're not going to get B alone or C alone. We're solving for that ratio. All right. Well, to get that alone, we're going to have to first of all undo this 6.1. So we'll subtract it from both sides, and we get 1.3 equals log base 10 of B over C, this ratio. I like looking at that 1.3 on this side, so I'm going to move it over there. And now we've got a log on one side, so we're going to drag down the result, throw the base to the other side, and apply the exponent. So it tells us that this ratio of B over C has to be this number. And if you use your calculator here, you end up with about 20. So the ratio is about 20 to 1. That ratio between bicarbonic and carbonic acid. All right, let's take a look at another one. All right, there's one more type of problem where logarithmic scale is used, and it's problems dealing with light intensity. Let's take a look at it. All right, here's a formula to deal with the magnitude of stars. Here it is, m equals 6 minus 2.5 log base 10 of L divided by L sub naught. Now, m is the magnitude of a star. Stars are given magnitudes up to 6, I believe it is. And L is the amount of light that's visible on Earth. Now, notice that we're not going to be talking about, whether there's, crud in the atmosphere that's causing the light to dim, or what the, so to speak, wattage is of that particular star. Is it putting out more light than any other star? We're simply going to be talking about how it's visible on Earth. It has nothing to do with how strong that star is, how fiery it is, or whatever. And L sub 0 is the amount of light that is being compared to. And normally stars are being compared to the dimmest star that's visible on Earth. Just like we normally compared sound to the smallest sound available, like a pin drop. So it's whatever it's being compared to. So it says in our problem here, if you look on the side here, this is on page 545, problem number 44. It says find the difference in the magnitudes of Sirius, that's a star, and the crescent moon. It says over on the side that the moon is 100 times brighter than Sirius. Okay, it's 100 times brighter than Sirius. This is a serious problem, I want to tell you. So if it's 100 times brighter, and they're asking for the difference, well, the difference means we're going to subtract. We're going to subtract the moon, magnitude of the moon, minus Sirius. Okay, so here we go. The moon is 6 minus 2.5 log base 10 of the moon, which we're going to let be 100 times, minus Sirius, which is 6 minus 2.5 log base 10 of, we're going to call it 1 because it's what it's being compared to. Okay? The difference between these two. Now notice if we were to look at this, we actually could write that ratio 100 over 1, because in fact This is subtraction here. We'll see that as we go through this. Now I need to distribute into this right parentheses here. So I'm going to bring this side down. This is negative 6 plus 2.5 log base 10 of 1. Well, notice that the negative 6 and the positive 6 will go out. And we end up with now turning both of these into a base of 10. So I'm going to go minus 2.5 log base 10 of 10 squared, that's 100, plus 2.5 log base 10 of 10 to the 0. Well, what is 10 to the 0? Well, 10 to the 0 is 1, but if I roll that 0 around to the front here, as we're multiplying, I'm going to end up taking 0 times all of this over here, and this ends up becoming 0. And if I roll the 2 around to the front here, minus 2.5 times 2, log base 10 of 10. Well, what is log base 10 of 10 if it's not just 1? So my answer here is minus 5, or we could say it's a difference of 5 magnitude star. The star's magnitude is 5. There's a couple of other ways to set this up where you would have ended up with a positive number here, but this tells us the difference between the two magnitudes. All right, so here's your assignment for tonight. I'm giving you some more practice problems that you need to solve. Please apply the properties there. We've already done 37 and 44 and 11 and 12, so that leaves 45 for you to do on calculating the difference in the magnitudes of Saturn and Neptune. So have a good time, enjoy yourself on this. Do the best you can. You can check your answers in the key. All right, have a good one. Talk to you later.